Okay, this is going to be the third video in a series of videos on center of mass. And in this video, what we'll look at will be a flat plate of uniform density, and it's a solid object that looks something like this. Now, if it's a flat plate with uniform density, it has a name, and the name is called a planar lamina, or just a lamina. However, in our video, we'll probably just refer to it as a flat plate. Now, the idea is this object could be made of any kind of material, and usually there's a density associated with it. So just to give it a number in our problem, let's suppose we have this. Usually the Greek symbol rho, so we'll use rho here. And suppose in our problem, it's 2 kilograms per square meter. So the area density is 2 kilograms per square meter. So that's what the mass of this object is going to be. Now, how do you approach a solid object? And again, it really helps if you look back at the previous video. So if you have not watched the video just before this one, I would definitely do that. And let's take a quick look at that. So this is what we had in the last video. We had a two-dimensional point mass system, and we used a series of steps to find the center of mass of this. Now let's take a quick look at each one of the 5 steps here. We'll scoot down. And again, if you definitely watch the video if you haven't done it. But it had 5 steps. And the idea is that you found the moment about the y-axis, you found the moment about the x-axis, you found the total mass of the system, then to find the x-coordinate of the center of mass, you took the moment about the y-axis divided by the total mass, and to find the y-coordinate, then you took the moment about the x-axis divided by the total mass. So it's actually a pretty easy series of steps to use. And again, going back looking at a picture of it, the idea is if you had a two-dimensional point mass system, this series of steps made it easy to find the center of mass. So how will this help you on the problem that we're looking at? So let's go back and take a look now at our problem. So we've got a solid object. Now, our approach is going to be to do this. We're going to take the solid object and break it up into a series of point masses. So we'll find an equivalent two-dimensional point mass system, and at that point, this problem will be exactly like the problem in the last video. So how do you go about doing this? And eventually we'll wind up working the same 5 steps to solve it, but we've got to do a little preliminary work first. So let's see what these preliminary steps look like. And I'm going to go ahead and put these up here. So the first thing you've got to do, you've got an object, and the very first thing to do is you have to establish a grid and define a series of individual geometric shapes. Now, when you pick your geometric shapes, you want to pick something that you can easily find the center of. For example, rectangles, circles, triangles, anything that you can easily locate the center of. And the first thing to do is to establish some sort of a grid. So take your object and put it on a grid. So let's go ahead and do that right now. And we'll look at some variations on this. So if we turn on the grid itself looks like this. Now, as far as establishing the grid goes, you can put it anywhere you want it. In this case, I put it at the lower left-hand corner, but just as easily, and let's go ahead and we'll kind of play around with this a little bit. If you wanted to, where you put the grid's up to you. So if you took your grid, and we'll change a couple things here first. If you took your grid and moved it, suppose I like it right here, and if I set it right here, I would get a good answer to the problem. But if you took the grid, and suppose you decide to scoot it from here, and you decide to center it maybe right here. Not a problem, you'll get a correct answer. Suppose you decided to move it up, and maybe you decided to center it right at this corner right here. That'll also work. So the point is, you can center the grid anywhere you want to, and you'll get a very good answer. So let's go ahead, and I think I'm going to move it right back down where I had it to start with. So I'll start it with it in the lower left-hand corner, about right here. So that's where my grid's centered, but your choice is where you center it where you want to. Okay, the next thing, define the individual geometric shapes, and because this thing essentially has rounded right angle corners, probably a series of rectangles. So what I'm going to do is break it up into, and you want to break it up into the smallest number of rectangles that you can to make the computations easier. So when I break this up, I'm going to go ahead and put my rectangles in like this. I'll make the first one be here. So there's the first rectangle. Second rectangle, I'll break into this little section right here. And then finally, the third rectangle, I'll put in this section over here. So I've got 3 rectangles. Now, even right here, I think I'll stop and show you one other alternative on this. Occasionally, I get some students that do this. there'll be two students that are sitting beside each other. One student breaks it up into three rectangles that look like this, and the student sitting right beside them might do something along this line. They'll break it up into some rectangles that say look like this. Now, in this case, we're going to use red rectangles. So suppose the second student decided to do it like this and put their rectangles on where they look and like this. So from there to there, over to here, to here, to here. So there's the first rectangle. And then from here down to here, all the way to this end, up to here, and then all the way across back to here again. And then the third rectangle, let's just say started at here and went up to here, like this, like this. So this student divides it up into a small rectangle here, one large rectangle in the bottom, and finally a pretty good sized rectangle up here. Now the question that they run across then is, will they get the same answer? And the answer is yes. So whether you use the three original black rectangles or these three red rectangles, or for that matter, you don't even have to use three. If you wanted to, let's do this. Suppose you decide to put another rectangle in right here. Now you've got four rectangles. If you wanted to divide this rectangle up into something, you could add an additional one. So you can use as many rectangles as you want to, but you want to try to use the smallest number just to minimize the computation. So anyway, in this case, we will stay with our three original black rectangles that look like this. So what we've done is we established a grid and we defined the individual shapes and put our rectangles on there. Okay, so the next thing we want to do then is to take each one of these rectangles and break them up into a series of individual point masses. And how do you do that? Well, that's what this next part is for. So for each rectangle, we'll find the center, the area, and the mass of each shape. In this case, our shape is a rectangle. So again, looking at this first one, and if you choose your grid correctly and use a small number of rectangles with easily recognizable shapes, you should be able to get the center in a lot of cases by just looking at your grid, which we can in this case. So what I want to do is find the center of this thing, and I'll go ahead and just put that on there. So the center of this thing, now it goes over 1. It's going to be halfway across, so it'll be at 0.5. And I think we'll go ahead and write this down here then. So for the first rectangle, the center is going to be it's going to go over 0.5 and up 2. So this is going to be 0.5 and 2. And that's going to be the center of the first rectangle. And let's go ahead and just put that on there. So there's the center of our first rectangle. Now I want the area of the first rectangle. So this is going to be, we'll call it area 1. So area 1 would be, and again, just the height times the width of the rectangle. So 4 high and 1 wide. It would be 4 times 1, which would be 4. And let's assume here that we're working in meters, so we'll call it 4 square meters. Now the next thing you want the equivalent mass of this thing. So if you were going to reduce this rectangle to a point mass, what would be the mass associated with it? So what the mass is, the mass of this rectangle is just the density times the area. So the density is, for all this, is 2 kilograms per square meter, and the area is 4 meters. So we've got 2 times 4, which gives us a total of 8. Now the units on this then would be kilograms. So 8 kilograms. So the mass of that first rectangle is, the equivalent point mass is 8 kilograms, and the center is at 0.5 and 2. So now let's go to the second one. So looking at the second one, the center, it goes from 1 to 5. The center would be at 3 over, and then it goes up to 2. So 3 over and up 1. So the center of this one's going to be right here, and we'll go ahead and put it on there. So the center of that second rectangle is right there. 3 and 1 will be the coordinates of that one. So this is going to have a center of x is equal to 3, y is equal to 1. I can get it right off the picture. Then you want the area. So what's the area of this second rectangle? Well, again, it goes from 1 to 5, so it's 4 units wide, and it's 2 units high. So I've got 4. The height would be 4. Or pardon me, the height would be 2. The width is going to be 1, or pardon me, 4. And that's going to give 8 square meters. So again, it's 2 by 4, so 8 square meters. Okay, the next thing I want is the mass of this second rectangle. And again, it's density times area. Well, the density is still the 2 kilograms per meter, square meter. And in this case, the area is 8 meters squared. So that's going to give you 16. The meters will cancel out, and it'll be 16 kilograms. So the mass of this one is 16 kilograms. And finally, let's get the mass of the third one. So first of all, the center of the third one. Now, where is that center located on our grid? Well, on our grid, the center would be 6, halfway between the 5 and the 7, and it goes up a total of 6. So over 6 and up 3, the coordinates of the center, and we'll go ahead and put that one on there. So there's the center of this thing, and it's located at the point 6 and 3. So I've got 6 and 3. There's the center of the third rectangle. Now, you need the area of the third rectangle. So the area of the third rectangle, and again, the area is just going to be the height times the width. Well, the height is 6. The width is 2, so it's going to be 6 times 2, which would be 12 square meters. So the area of this rectangle is 12 square meters. Then you want the mass. So what's going to be the equivalent point mass of this rectangle? And again, it's density times area. So the density is still 2. It's uniform density through the whole thing. This time you've got 12 square meters. And if you multiply that, you'd come up with 24 kilograms. Okay, now let's go ahead and write those on our figure here. So we've got is the first rectangle was reduced to an equivalent point mass of 8 kilograms. So we'll go ahead and put 8 kilograms right here. The second rectangle was reduced to an equivalent point mass of 16 kilograms. So that one's going to be 16. And finally, the third rectangle was reduced to an equivalent point mass of 24. So we'll put 24 on this one. So what those are, you've taken your original solid system and reduced it to an equivalent two-dimensional point mass system. So at this point, you really don't need the solid one anymore. So in a way, let's go ahead and do this. Let's go ahead and get rid of that where we can just concentrate on the point masses. So first of all, if we get rid of this gray shading, it'll reduce it to this. Now, this first rectangle has been reduced to a point mass, so we'll go ahead and eliminate that first rectangle. It's been replaced with this. The second rectangle has been reduced to this point mass, and finally this third rectangle has been reduced to this point mass. So what you've got now is a point mass system, and at this point, the entire problem is just like the problem in the last video. All you want to do is to find the center of a two-dimensional point mass system. So what we'll do is use exactly the same steps in the previous problem. So let's go ahead and turn these steps off and reintroduce the same steps that we had in the previous problem. And they look like this. Okay. So now, all you want to do, again, the 5 steps are find the total moment about each axis. So let's first of all go ahead and find the total moment about the y-axis by using the mass times the distance of each one. And again, I think it helps if you can actually see it on there. So let's go ahead and, well, first of all, just look at it like this. We want to go about the y-axis, and the y-axis goes from, it'll go from here down to here. So that's the y-axis. Now what the distance is from each point to the y-axis. So in this case, we're going to use horizontal distances. It'll be this distance here, and this distance here, and this distance from here to here. So what those would be in our system would be the mass of each object. So mass 1 times distance 1. So the first mass is 8 kilograms times the distance would be 0.5 plus the second mass is 16 kilograms and the distance is 3. And then finally, the third mass is 24 kilograms. So it's going to be 24. And the distance was 6. So that's going to be 6. So let's go ahead and solve that. So this is going to be 4 plus, and then 16 times 3 would be 48, plus 24 times 6 is 144. And if you added all that together, you would come up with 196. Now, the units are going to be kilogram meters. And that's going to be the moment of this system about the y-axis. So you've got, there's the moment about the y-axis. So now let's do the same thing, find the moment about the x-axis. So we will go with the horizontal axis in this case. So again, this time what we want would be this distance. We're going to go from here over to here. So there is the axis, but this time we want to use this distance from here to here, this distance from here to here, and this distance from here to here. So it looks like that. So this time it would be, and we'll go ahead and put those down here, it's going to be, the mass of the first one will be 8 times this distance, which is 2. So I've got 8 times 2 plus this mass times this distance, which would be 16 times 1. And then finally, I've got this mass times this distance, so 24 times 3. So this one's going to be 24 times 3. And we'll just concentrate just on those x distances this time. So this one's going to be 16 plus 16 plus 72. And if you add all these up, you'd come up with 104 kilogram meters. And what that's going to be the total moment about the x-axis. Okay, next thing you need, and again, we'll go ahead and get rid of these green ones now that we've used them. So we're back to just this system again. So the next step is to find the total mass of the entire system, and that's going to be pretty easy to do. It's just to add up these three masses. So you have 8 plus 16 plus 24, and if you add all those up, you'll get 48 kilograms. So that's the total mass of the whole system. Again, using the same steps in that previous video, to find the center of mass, the x-coordinate of the center of mass is just the moment about the y-axis divided by the total mass. So in that case, it would be the 196 kilogram meters divided by the total mass is 48 kilograms. And if you divide that, you would come up with 4.08 meters. And what this is the x distance, x coordinate of the center. Okay, find the center mass for the y, take the moment about the x-axis divided by the total mass. So that's going to be 104 kilogram meters divided by, again, 48 kilograms. And again, the kilograms will cancel out, and that's going to leave you with 2.17 meters. And what that is, that's the y location of the center of mass. Now, we've got this down. Let's go ahead and write those on our grid up here. So the x coordinate of the center turned out to be 4.08. And the y coordinate is 2.17. So that is going to be the center of mass. Let's go ahead and plot that on our system and see where that is. I think I'll do it in green. So I want to go over 4.08, which is about right here, and I want to go up 2.17, which would be about right here. So there's 3, there's 2, 2.17 would be about right here. So this whole thing's going to be about right in here. We'll put a little circle that looks like that. So what that is, that's the location of the center of mass of this system. Now, it helps sometimes to go ahead and put the original figure back on. So let's go ahead and turn that and put that back in here. So given this original gray system, the center of mass is going to be right where these green dots are. Now, what this actually is would be if you took a straight line from each one of these, let's go ahead and I think we'll put that on there. So if I went from here to here, and from the center of this one to here, and from the center of this one to here. So if you were to attach those 3 dots with a small wire, you could actually suspend it. It would balance on your finger right there. So what that is, that's an example of how to find the center mass of the system. Now just real quickly, let's kind of review the whole process again. The idea is that you started out with a solid mass you took that solid mass and broke them up into individual rectangles. So you had 3 individual rectangles that look like this. You then took each rectangle and found its center and its mass. So you changed it from a solid system into a point mass system. And then you used the 5 steps that we did in that previous video to identify the center of that point mass system. So actually, it's a fairly easy process, and the whole trick is just take whatever your original object is and break it up into smaller individual geometric shapes that you can easily find the center of. And if you do that, then it's actually a pretty easy process. So that's an example of how to find the center of mass of a solid flat plate, or what's called a lamina.